Okay, now we'll talk about heat engines. Heat engines, here's what heat engines do. They take heat from a hot reservoir, convert some of that to work, and then what it cannot convert, it has to dump out. Ideally, what you'd like to do is convert all of that to work, but of course you can't do that. I'm sorry? So in your car is about 20% efficient. For $5 of heat, you get $1 of motion.
Couldn't you make like an engine compartment out of like solar voltaic panels, which would absorb the heat and convert it to energy theoretically?
Yeah. You dump out the rest because it's no practical way. Right. $4 worth of heat is thrown out. The world's most efficient heat engine is a coal power plant. Nuclear power plants are about 35% efficient. For $100 of heat release, $35 is converted to electricity, $65 is thrown out. So that's why you got to build them. Where do you throw them out? Mostly in rivers and stuff like that. So large power plants are built near bodies of water, but nowadays you can dump the heat into the atmosphere as well. All right, so like I said, if the entire universe was at infinite temperature, well, you couldn't absorb heat because you would have to be at a lower temperature to absorb heat. And then, you can't dump. So that is the heat depth of the universe. Okay. If everywhere, you don't have to have infinite temperature. If everywhere the temperature was uniform, there's nothing that could be done. No heat could be converted into process. Okay, so life can only evolve where you have a temperature gradient. 5,800 degree Kelvin. That's the solar temperature, that's the temperature of the Earth. Okay? All right, so heat engines convert part of that heat to work. Okay? By the way, so this is do you want to see a animation for how a car engine works? Okay. Okay, what do you do in a car engine? You take gasoline, you burn it. The heat released with the heat released, you expand a piston which turns your car wheel. Okay? And then what do you have to do in practice? Well, when you burn gasoline that got converted to carbon dioxide and water vapor, you got to dump that out, clean your cylinder, then dump more gasoline. So you have to go through a cycle. Okay, so that's what you'll see.
I'm Jake O'Neill, creator of Animagraphs, and this is how a car engine works. Let's start with a single piston, the powerhouse of the engine, and work our way outwards. The four-stroke cycle. When a piston travels to the end of its range, whether up or down, that's a stroke. Car engines use a four-stroke cycle, and it goes like this. First, intake. The piston descends, sucking an air-fuel mixture into the cylinder through the intake port, with both intake valves open. Next, compression. When a piston travels to the end of its range, whether up or down, that's a stroke.
Sorry.
And work our way outwards. The four-stroke cycle. When a piston travels to the end of its range, whether up or down, that's a stroke. Car engines use a four-stroke cycle, and it goes like this. First, Intake. The piston descends, sucking an air-fuel mixture into the cylinder through the intake port, with both intake valves open. Next, compression. With all valves closed, the piston comes back up, compressing the fuel and air mixture for more powerful combustion. Then, the power stroke. An electrical spark ignites the compressed fuel and air mixture, and the resulting combustion forces the piston to the bottom of the cylinder again. A connecting rod transfers this power to the crankshaft. Finally, exhaust. The piston comes back up, pushing the spent mixture out through open exhaust valves and the exhaust port, connecting multiple pistons. For smooth power delivery, pistons take turns firing. The firing order for this engine is 1, 3, 4, 2.
All right, so you took the piston expanded, you took in the air-fuel mixture, then you compress that. Why do you compress it? You warm the air. You want to make sure that every gas molecule burns. Okay, you want as much of the fuel to burn. All right, so you have this anti-knocking problem. If you compress it too much and the gas heats up too much, it might self-ignite without the use of spark plug, part of the gas. Then if it's self-igniting, well, it's working against this piston coming up. You're wasting energy. Okay? So you want all the gas to compress and then the ignition to happen. Okay? So diesel engines, what they do is to prevent anti-knocking, and you learn that the efficiency is higher the more the compression you get. So diesel engines, what they do is they just compress plain air. Air is warmed up and then they squirt in the diesel, and you don't need the spark plug. The diesel ignites in the hot gas, and then no heat is wasted. Okay? When you generate the heat, when the gasoline is burnt and you generate the heat, that is what's pushing. That's where the heat is being converted to work, on that stroke. And then of course you gotta get rid of all the burnt stuff, which is the next cycle. Okay, so that's what's happening. All right. So a heat engine takes heat, absorbs heat from a hot reservoir, converts part of that to work, and dumps the heat that it cannot do anything with into the environment. Okay, so the exhaust, what is the cold reservoir for when you're driving the car? The outside air. Okay? And that's where you're dumping the exhaust gases. Okay, the efficiency of a heat engine is how much work you got out of it by absorbing this much heat. That's the efficiency of a heat engine. Okay? Of course, you want this to be 1, but you can forget about that. Okay? So Mr. Carno asked the following question. Let's say you're building a heat engine, and Mr. Carno asks, what is the maximum efficiency I can get? And the answer he found was surprising. So of course, what kind of engine will get the maximum possible efficiency? An ideal heat engine. Okay? So you think of an ideal heat engine. So this is an engine in your mind. It's not a practical engine. And it's going to give you an upper limit. Okay? So Mr. Carno thought of a heat engine, ideal engine. All processes are reversible. Are there any processes in nature that are reversible? No. Reversible processes are frictionless processes and all that. Okay? And here is Carnot's. So the working gas would go through an isotherm, an adiabatic process, an isotherm, and an adiabatic process. That's the cycle it would go through. Okay? Yeah. real engines are less efficient than the ideal engine, of course. So Carnot's engine just establishes an upper limit. Okay? So this is a mental concept, and the idea is to. So here's a Carnot engine. Its efficiency is greater than all real engines. That's the point.
Comparison.
I'm sorry?
For comparison.
No, to set an upper limit. Okay. All right. Okay, so for a heat engine, for any old heat engine, you absorb heat, convert some of that to work, and dump the rest. How much work did you convert? This is the amount of heat you absorb. QH is the heat absorbed from the hot reservoir, and QC is the heat dumped to the cold reservoir. Okay. Efficiency is W over that. So for all engines, the efficiency is 1 minus QC by QH. 1 minus the QC is the heat dump. This is the heat absorbed. And here's the surprising result Mr. Carnot found. Mr. Carnot found that for his engine, his ideal engine, this was equal to TC over TH. It just depended on the temperature at which you're operating. It doesn't depend on how you made it, how the engine is made. So, for an engine operating between these two temperatures, here is the upper limit to the efficiency. This is the cold temperature, the temperature at which you're dumping out your exhaust heat, and this is the temperature at which you're absorbing the heat. Okay. So for instance, if you wanted an efficiency of 1, you can absorb heat from an infinite temperature reservoir. Okay. And then, if your car cylinder, inside the car cylinder, the temperature was infinite, then your car would be 100% efficient.
Or if the cold was absolute zero?
Yep. Or if you're dumping drive in somewhere in Alaska, your efficiency increases. Okay. All right, so the amazing part is for an ideal heat engine, the efficiency depends on only the operating temperature. Okay. In a Carnot engine, so for a Carnot engine, QH by TH, this is what Mr. Carnot showed. Okay. So the efficiency is equal to 1 minus QC by QH, and QC by QH from this equation is TC by TH for a Carnot engine. Okay. So the efficiency of all real engines is less than 1 minus TC by TH. Okay. So this is the maximum possible efficiency for a heat engine. If your car engine were a Carnot engine, its efficiency would be about 70%. So if your car engine was an ideal engine, the temperature at which it's operating, its efficiency should be 70%. Your actual efficiency is about 20-25%. So in practice, you're losing a lot of heat to leakage and all that kind of stuff, and friction and all that. See, there's a lot of room for improvement, and I'm sure there's plenty of people working hard. So heat to work conversion is very inefficient. You guys know how efficient electric cars are? 90%. Right. So the internal combustion engine is dead.
Isn't there a process where?
So in the future, what is it that you want to do? Use solar cells to produce electricity, charge your batteries, and drive your car. I'm sorry, go ahead.
Aren't there like thermoelectric generators?
Yeah, there are.
So then wouldn't we be able to, like, when the heat that's not harnessed into work, go?
Well, you don't want your life to depend on burning stuff. Because that route is very inefficient, yes?
What about rocket engines? How efficient are they?
And they're not efficient. But those are rich person toys. In practice, when you want billions of people to live on, then you want solar and wind. All right? All right, so you saw, we saw a brief picture of heat engines. Now we'll talk about refrigerators. What do these guys do? I'm sorry?
Whole heat from the system.
Yeah, so, well, that's colloquially used, but you really, yep, okay. So what a refrigerator does is, so here's your kitchen, which is at 30 degrees Celsius, and inside your refrigerator it's 4 degrees Celsius, something like that. You bring in a 6-pack and put it in there. And what you want to do is remove heat from here to there. So in a refrigerator, you have to remove heat from a colder place and dump it in a hot place. Of course, nature won't do this, so you have to do work to do that. Okay. And how do you do work? Your refrigerator is plugged in, and the compressor is doing the work. Yeah. Now, the instant you unplug the refrigerator, that will stop. Now the question is still, how do you do this in practice? How do you remove heat from here and then put it there?
Use some sort of gas or refrigerant.
Okay. So,
Evaporation.
very good. That's the key. Did you guys hear that? So, evaporation is the key. Okay, so let me remind you guys of the latent heat of vaporization. Okay, so to convert 1 gram of water to steam, when you convert 1 gram of water to steam, it absorbs 540 calories of heat. Okay. So, in principle, here's inside your refrigerator, here's a pipe, and this was water, and somehow you convert that to steam, it'll absorb 540 calories of heat. That has become steam, you bring it out, and then you pass it through a compressor, the steam, so this is water, steam, pass it through a compressor, turn it back into water. What happens when you convert steam into water? It gives up 540 calories of heat. See, you removed heat from here and dumped it outside. That was your goal. Okay, so a liquid coolant evaporating absorbs heat, and then the vapors compress back to the coolant, dumps out the heat out here. So that's the process. Of course, you're not using water, you're using some kind of coolant. Okay? And the kind of coolant, so that's the process. Okay? Everybody understand that? And then you cycle that back through again. Okay? So here's the choice of the coolant. Okay? So here the evaporator, all this is in a closed cycle. When the liquid evaporates, it absorbs heat, it comes out, and then it is compressed again, high pressure vapor compressor. It anyway, you convert back into liquid, and then the heat is dumped out. Okay. The coolant is vaporized in the evaporator. The vaporizing coolant extracts heat from the refrigerator. It is then compressed and sent through a condenser where it exhausts heat to the outside. Okay. Yeah. So the vapors come here, and then high pressure vapor radiator, it removes heat, and then that becomes fluid. Okay. Here's how you decide what coolant you want. So a heat pump is also a refrigerator. What does a heat pump do? So what does a heat pump do? A heat pump, right now it's cold. It will extract heat from the cold air outside and dump it in this room, okay, into a warmer room. So same thing, it's extracting heat from the outside from a cold temperature and dumping it here. Air conditioners and refrigerators are heat pumps as well. Okay. Whoa. Okay, a coolant with a boiling temperature below the freezing point of water is used. Okay, so if you want in a freezer, what is the temperature you maintain? Minus 20 degrees Celsius. So in a freezer, to get to that temperature, you would have to use a coolant whose boiling temperature was below that temperature. Okay, did you guys understand? So let's say if you want to maintain a minus 30 degrees Celsius someplace, if you want to cool it down to that, what you want is a coolant whose boiling point is minus 40 degrees Celsius. Okay. So that's how it works. Okay. All right, next time you go to buy a refrigerator, here's what you want to look for. Okay, what are you doing in a refrigerator? You're removing heat from a cold reservoir. And to do that, you have to do work. And then dump that heat into your kitchen. So this is the inside of the refrigerator from where you're removing the heat. Your refrigerator is plugged in, and you're dumping that heat into your kitchen. All right, what is it that you want? You want to remove heat. And what is the price you're paying? This is the price you're paying. Okay, so that's what you want, and that is the price you're paying. And it turns out that typical household refrigerators have a coefficient of performance of 5. That is, you're removing 5 joules of heat, and you're having to do 1 joule of work. And remember, that's what your car does too. 5 joules of heat, and it converts 1 joule to work. Okay. And so just like the Carnot engine, which gives you an upper limit, here's a coefficient of performance for an ideal refrigerator, which is that just depends on the temperature. Okay. All right, guys, so the appendix has a bunch of stuff. This shows you, okay, I'll show you one thing. Remember I said that you can calculate, so this is something, if you were a physics major, you would be interested in. Calculating the entropy of a system is very hard. It's a state function. This is the Boltzmann's constant, and that is the number of microstates for a given macrostate. So the microstate, for instance, the gas in this room, how many gas molecules are there? 10 to the 28 gas molecules. Okay, and how many different ways can you arrange them? How can you distribute the energies in this gas? I mean, that would be an enormous number. Okay, and calculating that will be quite hard. But anyway, if you could calculate that, the entropy of the gas in this room would be K times log of W. Mr. Boltzmann was a very smart dude. Yeah, yeah,
This one
yeah,
was
yeah,
inside,
yeah,
it's full.
yeah. So for a smaller, and look at this, that's the formula he's most proud of. Yeah. All right, fellas, so there's other stuff in there, but you guys can read the appendix, okay?